Hi. Oh, hi. I've been saying hello and hi and stuff. But now I'll say it again. Thank God it's Thursday. And hello, Coffee. Hello, Ed. Hello, Coffee. Twitch version and YouTube version. What's up? Thank you for stopping by. And I do realize that I am 1 hour streaming 1 hour later than usual, which is, happens. Life. Okay, so I didn't test if my I'm showing the correct screen, and if I'm not, then I'm gonna be real sad about it. Let's try. I technically finished Tiny Sherlock, but that does not mean I understand what I did. Ya Allah. Ooh, it's correct. I mean, the only thing I did is run it, so yeah, I had higher hopes, but also it's cool. It's pretty cool. Like one would expect Sherlock to always be, I don't know, like I feel like I've disappointed Sherlock, but that's okay. All right, yes, some code cleanup happened, and then we're gonna learn about self-attention. I am still continuing with this one here. There's something wrong with it copying my face because it keeps saying I can't find you. Can you find me now? Okay. Find me. Anyway, refresh, and how are your days going? I hope well. Yes, I had a funny day yesterday. Like yeah, I wouldn't say a bad day, but like an odd day for sure. Let's see how it goes. It's a small language model. True. All you can expect is like Sherlock flavored. That is absolutely true. Text that's mostly incoherent. Yes, it was incoherent flavored Sherlock. I didn't get elementary, my dear Watson, but I got some yeah. It felt Sherlocky. Can we hear audio?
So this is probably the most important part of this video to understand.
Oh, yes, we can hear audio, and it is the most important part. So, 집중 means focus. Oh, I think 집중. Yes, 집중하자. Let's focus.
Understand. We're going to implement a small self-attention for a single individual head, as they're called. So we start off with where we were. So all of this code is familiar. So right now I'm working with an example.
So is this code familiar? The seating, okay. This is we gave them for funsies, okay. We do this is that this rand n. I might misremember, but I have a vague notion that famous phrase isn't actually used that much in the stories. No. Yeah. It's almost like I don't think it's the level of Luke, I'm your father. As in like, but yeah, it is something that probably was made famous by shows and TV and movies. I also think that's the case. Maybe it's once, but it is part of the whole canon. Maybe not the text canon. I'm not sure, but I agree with you. It not being such a big deal. So we have this this matrix here, and then we This is the weight. Okay, I forgot. And then we have max, and then we have softmax. Let's see.
Where I changed the number of channels from 2 to 32. So we have a 4x8 arrangement of tokens, and and the information at each token is currently 32 dimensional, but we just are working with random numbers.
Ah, okay, cool. So this is size, and then we make it random numbers. Hi, Lisa K. Liz K. Sorry, why did I make it Lisa? Thank you. I will try to have a good day today. It's not a busy day, but it is like there are a bunch of stuff I should do. I wish you a good day as well. If it's day and if it's almost evening, then good rest of whatever time is left.
Now we saw here that the code as we had it before does a simple average of all the past tokens and the current token. So it's just the previous information and the current information is just being mixed together in an average. And that's what this code currently achieves. And it does so by creating this lower triangular structure.
Right. We are doing the thing where it starts off being the number itself, and then the next number is the number before it and itself, and then all the way down. I don't know why I'm calling it rolling average. I might be wrong. Don't sue me yet. Later. You can do that.
Which allows us to mask out this weight matrix that we create. So we mask it out and then we normalize it. And currently, when we initialize the affinities between all the different sort of tokens or nodes, I'm going to use those terms interchangeably. So when we initialize the affinities between all the different tokens to be 0, then we see that way gives us this structure where every single row has these uniform numbers. And so that's what then in this matrix multiply makes it so that we're doing a simple average. Now, we don't actually want this to be...
X is the random thing, and then we have the weight. Oxford references elementary modern Watson is never used. Okay, so it is exactly the level of look, I am your father. Cool. Oh well, don't know my location. That's rude. Memories of Sherlock Holmes. Excellent. I cried elementary. And he said, is recorded. Oh wow, so far. Whoa. That's like 100 years ago. I can't imagine 100 years ago. I mean, I've seen the colorized videos on like Reddit. Sometimes they come up. Oh my god, they are so cool. Yeah. 100 years later, people will be like, I hope they will say that we were cool and not cruel to the environment and
all uniform, because different tokens will find different other tokens more or less interesting, and we want that to be data dependent.
Oh, sorry, I forgot to explain to myself that this part is we want them to sum up to 1. That's the weight. Each row sums up to 1, and then we do the thing. Okay.
So, for example, if I'm a vowel, then maybe I'm looking for consonants in my past, and maybe I want to know what those consonants are, and I want that information to flow to me.
Okay. Hard to imagine a world without fridges and washing machines. Washing clothes used to be a lot of work. I mean, can I imagine? Do I remember when we got our first washing machine? I think I do. Barely, though, barely. I feel like fridges. Okay, let me try and show that it wasn't to that level, because as far as I know, there used to be at least some sort of type of food storage place. Maybe not like, now I'm thinking like London 100 years ago, which was industry, too much smoke, all of that. But like if I think a village, then I think there were some sort of food storage in different, like literally the other, I would say day, but like a few weeks ago, my mom was talking about how food used to be stored in animal skin and they would not go bad. So yeah, grandma lived in an old house that had been her mother's, still had the outdoor washroom. See, they had stuff. They had stuff. Stone mangle. Whoa. And yeah, people used to wash clothes with hands, but I also think there were some stuff that would help with, I don't know. But food storage, they had it figured out. Or at least they would have made it dried. Hello, hello, JSS. We are talking about we are on a tangent. Just yeah, food storage, and I guess cleanliness was not as prioritized, maybe, but like 100 years ago now, the world was recovering from World War One, right? So probably a lot of sickness. Had an outdoor. Oh wow, flushing toilet. Oh yeah, that's scary to use at night. Yeah, ooh, I know. I've actually been 50 meters. That's pretty, that's good for the smell though. It being pretty far. I have been to like places where the restroom is outside, and yeah, when you go at night, you have to be careful with bugs and mosquitoes. I wouldn't say the level of bugs that maybe some countries have, but mosquitoes, 100%. Spiders, definitely. Scorpions, yeah. Yes, I understand the toilet being too far. I mean, I'm saying I've been places that has had that, not that have lived there. Just like going there for a trip, overnight trip. Yeah. Yeah. Yes. I mean, we have been through the no internet world, so we know changes, but I don't know. I can't, yeah. Snakes. Snakes. We have some snakes sometimes. Like once a year we get a snake. I think they have some sort of schedule. Yeah. We have bugs, but we have cats. Yeah. We have mice and the cats eat the mice. Yes. And then we have tensors. I like the word tensor. Feels science fiction.
And so I want to now gather information from the past, but I want to do it in a data-dependent way. And this is the problem that self-attention solves.
So the other ones were not caring about context as much. They sort of were.
Now, the way self-attention solves this is the
Oh wow, look at you. Wow. Just bringing it back. Yes, the python eats the tensor. Can tensors be eaten? Aren't they, depending on the dimension? Each time I think about different dimensions, I remember that Carl Sagan video. It is so cool. I mean, I shouldn't go on more tangents, but there's a Carl Sagan video about dimensions. Die. Oh, what is that? Whoa. There's an introduction to Transformers with Andre Karpathy. video on Stanford's YouTube, and it's being recommended to me. Dimensions, Carl Sagan. This video. We're not gonna watch it, but there's a 7-minute version, there's a 9-minute version, and then I'm gonna drag it here for a second, and then should check the doc on. Huh? There are no rules about eating tensors, but yeah, see this video. He starts off saying, I mean, you have to watch it. I will not give it, yeah. So these are two-dimensional things living in their two-dimensional lives. This is a house, and then they see a three-dimensional object coming in, the apple, and they can't see it when it's above, but when it reaches them, they can only see this part of like the slice. See? So cool. I'll put this in the chat because it's a really cool video. Like you can just share it with a kid and have them be like, whoa. Okay. Tensors. Let's go.
Following. Every single node, or every single token at each position will emit two vectors. It will emit a query, and it will emit a key. Now, the query vector, roughly speaking, is what am I looking for? And the key vector, roughly speaking, is what do I contain?
Oh.
And then the way we get affinities between these tokens now in a sequence is we basically just do a dot product between the keys and the queries. So my query dot products with all the keys of all the other tokens, and that dot product now becomes way. And so if the key and the query are sort of aligned, they will interact to a very high amount, and then I will get to learn more about that specific token as opposed to any other token in a sequence.
Cool. So we have to rewrite this line. Cool.
So let's implement this now.
Oh.
We're going to implement a single,
What are you writing?
what's called head of self-attention.
Okay.
So this is just one head. There's a hyperparameter involved with these heads, which is the head size. And then here I'm initializing.
Okay. Based on the channel?
Linear modules, and I'm using bias equals false, so these are just going to apply a matrix multiply with some fixed weights. And now let me produce a key and Q, K and Q, by forwarding these modules on X. So the size of this will now become B by T by 16, because that is the head size, and the same here, B by T by 16. So this being the head size. So you see here that when I forward this linear on top of my X, all the tokens in all the positions in the B by T arrangement, all of them in parallel and independently produce a key and a query. So no communication has happened yet. But the communication comes now. All the queries will dot product with all the keys. So basically,
what questions I have? Are we going to make this later? Or is the linear thing a function itself so that we can give it X? And X is the random. And based on the linear, it will be updated. I think so. Right?
what we want is we want way now, or the affinities between these, to be query multiplying key. But we have to be careful with, we can't matrix multiply this. We actually need to transpose k. But we have to be also careful because these are when you have the batch dimension. So in particular, we want to transpose the last two dimensions, dimension -1 and dimension -2. So -2, -1. And so this matrix multiply now will basically do the following. B by T by 16 matrix multiplies B by 16 by T to give us B by T by T. Right?
Okay.
So for every row of B,
This T should talk with this, and this is talking with this. Is that the case?
we're now going to have a T square matrix giving us the affinities. And these are now the way. So they're not zeros. They are now coming from this
This is the way now. Cool.
Dot product between the keys and the queries. So this can now run. I can run this. And the weighted aggregation now is a function in a data-dependent manner between the keys and queries of these nodes. So just inspecting what happened here, the way takes on this form. And you see that before way was just a constant. So it was applied in the same way to all the batch elements. But now every single batch elements will have different sort of way, because every single batch element contains different tokens at different positions. And so this is now data dependent. So when we look at just the 0th row, for example, in the input, these are the weights that came out. And so you can see now that they're not just exactly uniform.
And they're not summing up to something. Like we're not requiring that.
And in particular, as
Are we? Because I see, oh, it is though. It actually is. Okay, everything is summing up to 1. Now that I look at it, I thought this was an 0.5 where there are more, but no, this is an 0.05. Cool.
an example here for the last row, this was the 8th token. And the 8th token knows what content it has, and it knows at what position it's in. And now the 8th token, based on that, creates a query. Hey, I'm looking for this kind of stuff. I'm a vowel, I'm on the 8th position, I'm looking for any consonants at positions up to 4. And then...
Why does this look like, you know, those online dating videos of like the 1990s? I'm looking for this. That's fun.
all the nodes get to emit keys. And maybe one of the channels could be, I am a consonant, and I am in a position up to 4. And that key would have a high number in that specific channel. And that's how the query and the key, when they dot product, they can find each other and create a high affinity. And when they have a high affinity, like say, this token was pretty interesting to this 8th token. When they have a high affinity, then through the softmax, I will end up aggregating a lot of its information into my position. And so I'll get to learn a lot about it. Now, just this, we're looking at way after this has already happened. Let me erase this operation as well. So let me erase the masking and the softmax, just to show you the under the hood internals and how that works. So without the masking and the softmax, way comes out like this, right? This is the outputs of the dot products. And these are the raw outputs, and they take on values from negative, 2 to positive 2, etc. So that's the raw interactions and raw affinities between all the nodes. But now, if I'm a 5th node, I will not want to aggregate anything from the 6th node, 7th node, and the 8th node. So actually, we use the upper triangular map.
So that it only sees what's in the past and not in the future. This is what this masked fill does. Okay.
Masking. So those are not allowed to communicate. And now we actually want to have a nice distribution. So we don't want to aggregate negative 0.11 of this node. That's crazy. So instead we exponentiate and normalize. And now we get a nice distribution that sums to 1. And this is telling us now in a data-dependent manner how much of information to aggregate from any of these tokens in the past. So that's way, and it's not zeros anymore, but it's calculated in this way. Now there's one more part to a single self-attention head. And that is that when we do the aggregation, we don't actually aggregate the tokens exactly. We produce one more value here, and we call that the value. So
key query and value.
The same way that we produced key and query, we're also going to create a value. And then here, we don't aggregate x. We calculate a v, which is just achieved by propagating this linear on top of x again. And then we output way multiplied by v. So v is the elements that we aggregate, or the vector that we aggregate, instead of the raw x.
Hello. Hi, Sayed. Shadi. Can you tell me how your name is pronounced? It's that okay with you? Should I just go with Sayed? So value. Where did we get value? Oh, same thing. Huh. I'm gonna go back
So in the same way that we produced key and query, we're also going to create a value. And then here, we don't aggregate x. We calculate a v, which is just achieved by propagating this linear on top of x again. And then we output y multiplied by v. So v is the elements that we aggregate, or the vectors that we aggregate instead of the raw x. And now, of course, this will make it so that the output here of this single head will be 16-dimensional, because that is the head size. So you can think of x as kind of like private information to this token.
So value is the key. They start off being the same, but I don't know why they can't be, because now we are having k and q become the weight, and then the weight gets multiplied by different projections by the value, and that becomes the output. So these two get merged, and then we talk with this, but they start off all being the same. Like right now, everything is the same. Yeah.
If you think about it that way. So x is kind of private.
Let me go back.
Private
Okay.
is the head size. So you can think of x as kind of like private information to this token, if you think about it that way. So x is kind of private to this token. So I'm a fifth token at and I have some identity, and my information is kept in vector x. And now, for the purposes of this single head, here's what I'm interested in. Here's what I have. And if you find me interesting, here's what I will communicate to you. And that's stored in v. And so v is the thing that gets aggregated for the purposes of this single head between
Like the dot product of the query and key is a scalar, I think. So it gets multiplied with the value to go back to being a vector. This is the output of the dot product, no? Okay. So we said key is what I have, query is what I want, and value, like just saying them abstractly, what I will communicate? Huh.
And so v is the thing that gets aggregated for the purposes of this single head between the different nodes. And that's basically the self-attention mechanism. This is what it does. There are a few notes that I would like to make about attention. Number one, attention is a communication mechanism. You can really think about it as a communication mechanism where you have a number of nodes in a directed graph where basically you have edges pointed between nodes like this. And what happens is every node has some vector of information, and it gets to aggregate information via a weighted sum from all of the nodes that point to it.
Weighted sum, okay.
And this is done in a data-dependent manner. So depending on whatever data is actually stored at each node at any point in time. Now, our graph doesn't look like this. Our graph has a different structure. We have 8 nodes because the block size is 8, and there's always 8 tokens. And the first node is only pointed to by itself. The second node is pointed to by the first node and itself, all the way up to the 8th node, which is pointed to by all the previous nodes and itself. And so that's the structure that our directed graph has, or happens to have, in an autoregressive sort of scenario like language modeling. But in principle, attention can be applied to any arbitrary directed graph, and it's just a communication mechanism between the nodes. The second note is that notice that there's no notion of space. So attention simply acts over like a set of vectors in this graph. And so by default, these nodes have no idea where they are positioned in the space. And that's why we need to encode them positionally and sort of give them some information that is anchored to a specific position so that they sort of know where they are. And this is different than, for example, from convolution, because if you run, for example, a convolution operation over some input, there's a very specific sort of layout of the information in space, and the convolutional filters sort of act in space. And so it's not like in attention. In attention is just a set of vectors out there in space. They communicate, And if you want them to have a notion of space, you need to specifically add it, which is what we've done when we calculated the positional encodings and added that information to the vectors.
Did we do that? Positioner? I don't think we did that. Query and key is what I'm looking for pairwise. I am and want. And value is what I want communicate back to me. Ah, if I see them? I don't know, but I will agree with you for now because it makes some sense to me right now. Huh? I really should put the loading thing on my brain because like my brain is like just running around in circles, but yeah.
The next thing that I hope is very clear is that the elements across the batch dimension, which are independent examples, never talk to each other. They're always processed independently. And this is a batched matrix multiply that applies basically a matrix multiplication kind of in parallel across the batch dimension. So maybe it would be more accurate to say that in this analogy of a directed graph, we really have, because the batch size is 4, we really have 4 separate pools of 8 nodes, and those 8 nodes only talk to each other. But in total, there's like 32 nodes that are being processed. But there's sort of 4 separate pools of 8. You can look at it that way. The next note is that here in the case of language modeling, we have this specific structure of directed graph where the future tokens will not communicate to the past tokens. But this doesn't necessarily have to be the constraint in the general case. And in fact, in many cases, you may want to have all of the nodes talk to each other fully. So as an example, if you're doing sentiment analysis or something like that with a transformer, you might have a number of tokens, and you may want to have them all talk to each other fully, because later you are predicting, for example, the sentiment of the sentence. And so it's okay for these nodes to talk to each other. And so in those cases,
we should, sorry, I shouldn't interrupt him, but we should say how many nodes should talk to each other. Otherwise, it becomes too costly and resource intensive, question mark.
You will use an encoder block of self-attention. And all it means that it's an encoder block is that you will delete this line of code, allowing all the nodes to completely talk to each other. What we're implementing here is sometimes called a decoder block. And it's called a decoder because it is sort of like decoding
going back to
language,
the original.
And it's got this autoregressive format where you have to mask with the triangular matrix so that nodes from the future never talk to the past because they would give away the answer. And so basically in encoder blocks, you would delete this, allow all the nodes to talk. In decoder blocks, this will always be present so that...
Oh, that makes sense. This is the thing that makes it only see the past. But if we don't have this, then it will see everything. That's cool. Things are making a level of sense to me.
You have this triangular structure. But both are allowed, and attention doesn't care. Attention supports arbitrary connectivity between nodes. The next thing I wanted to comment on is you keep me...
What if we make it only see the future? Would it become some sort of... My brain is going, Madam Web.
You keep hearing me say attention, self-attention, etc. There's actually also something called cross-attention. What is the difference? So, basically, the reason
this is self-attention, because the key is like me, and value is, yeah, okay.
This attention is self-attention, is because the keys, queries, and the values are all coming from the same source, from X. So the same source X produces keys, queries, and values. So these nodes are self-attending. But in principle, attention is much more general.
They grew up with busy parents, so they have to be self-attending. You could train it to write backwards. Why not? I mean, my brain just went, that's like writing Arabic. It's backwards from English, but that's wrong. Yeah, reverse. Like, it should, it's, I can't even imagine. You only want learning on a certain point, relevant point. Yeah. Yes. There's a reason why we use the past only, but I don't know why. I'm like, what happens if we do future only. But it doesn't make sense though. It doesn't make sense. Whoa. This you can't see it. Oh. Can you see it? No, you can't see it. Okay. This thing here, arrow, was merging with the arrow of the pointing down, and it looks really cool.
Than that. So for example, in encoder-decoder transformers,
Mhm.
you can have a case where the queries are produced from X, but the keys and the values come from a whole separate external source, and sometimes from encoder blocks that encode some context that we'd like to condition on. And so the keys and the values will actually come from a whole separate source. Those are nodes on the side, and here we're just producing queries, and we're reading off information from the side. So cross-attention is used when there's a separate
Neighboring nodes? Who are they? Why are we taking their keys and values or queries?
source of nodes we'd like to pull information from into our nodes. And it's self-attention if we just have nodes that would like to look at each other and talk to each other. So this attention here happens to be
Yeah, you're right. Answer obviously needs past relevance. I think I was just trying to make a joke that didn't land.
self-attention. But in principle, attention is a lot more general. Okay, and the last note at this stage is, if we come to the attention is all you need paper here, we've already implemented attention. So given query key and value, we've multiplied the query and the key, we've softmaxed it, and then we are aggregating the values. There's one more thing that we're missing here, which is the dividing by 1/square root of the head size. The dk here is the head size. Why are they doing this? Why is this important? So they call it a scaled attention. And it's
For the no pose paper, the mask might help the model understand the directionality of the text. GPT models really didn't suffer much without POS. Is that supposed to be part of speech? Decoding, but BERT-style models barely learned. It's convenient to mask the future. Yeah, for generation, right? It helps train in parallel, but the model can't cheat and get information from future to just position. Thank you. Okay. Look up what it's meant to predict. Yeah. Yep. Both masked feeling and just not seeing the future are like on purpose. Yep. Position encoding so that it knows where things are.
kind of like an important normalization to basically have. The problem is if you have unit Gaussian inputs, so zero mean, unit variance, K and Q are unit Gaussian, then if you just do way naively, then you see that your way actually will be, the variance will be on the order of head size, which in our case is 16. But if you multiply by 1/head size square root, so this is square root and this is 1/, then the variance of way will be 1, so it will be preserved. Now, why is this important? You'll notice that way here will feed into softmax.
Yes.
And so it's really important, especially at initialization, that way be fairly diffuse. So in our case here, we sort of lucked out here, and way had a fairly diffuse numbers here.
Yep.
So like this. Now the problem is that because of softmax, if way takes on very positive and very negative,
Perplexity goes way down to 0 if the model can just cheat and see the answers. That would be just like super overfitted, right? If that's like the way that we would say. It would just like memorize everything and then regurgitate it back to you.
numbers inside it, softmax will actually converge towards one-hot vectors. And so I can illustrate that here. Say we are applying softmax to a tensor of values that are very close to 0, then we're going to get a diffuse thing out of softmax. But the moment I take the exact same thing and I start sharpening it, making it bigger by multiplying these numbers by 8, for example, you'll see that the softmax will start to sharpen. And in fact, it will sharpen towards the max. So it will sharpen towards whatever number here is the highest. And so basically we don't want these values to be too extreme, especially at initialization. Otherwise,
It will stop being a softmax and start being a sharpmax.
softmax will be way too peaky, and you're basically aggregating information from like a single node. Every node just aggregates information from a single other node. That's not what we want, especially at initialization. And so the scaling is used just to control the variance at initialization. Okay, so having said all that, let's now take our self-attention.
I understand stuff to a level, and now I need to like hold my head so that the information does not leak out. It might.
Knowledge, and let's take it for a spin. So here in the code, I've created this head module, and it implements a single head of self-attention. So you give it a head size, and then here it creates the key, query, and the value linear layers. Typically, people don't use biases in these. So those are the linear projections that we're going to apply to all of our nodes. Now here, I'm creating this trill variable. Trill is not a parameter of the module. So in sort of PyTorch naming conventions, this is called a buffer. It's not a parameter. And you have to call it, you have to assign it to the module using a register buffer. So that creates the trill, the lower triangular matrix. And when we're given the input x, this should look very familiar now. We calculate that.
Sharpermax being Sharpie. Smart. Yeah, sure. My brain went Sharpay from High School Musical. I don't think she would like this.
Keys, the queries, we calculate the attention scores inside way. We normalize it, so we're using scaled attention here. Then we make sure that future doesn't communicate with the past, so this makes it a decoder block. And then softmax, and then aggregate the value and output. Then here in the language model, I'm creating a head in the constructor, and I'm calling it self-attention head. And the head size, I'm going to keep as the same and embed, just for now. And then here, once we've encoded the information with the token embeddings and the position embeddings, we're simply going to feed it into the self-attention head, and then the output of that is going to go into the decoder language modeling head and create the logits. So this is sort of the simplest way to plug in a self-attention component into our network right now. I had to make one more change, which is that here in the generate, we have to make sure that our IDX that we feed into the model, because now we're using positional embeddings, we can never have more than block size coming in, because if IDX is more than block size, then our position embedding table is going to run out of scope because it only has embeddings for up to block size. And so therefore I added some code here to crop the context that we're going to feed into self, so that we never pass in more than block size elements.
Okay.
So those are the changes, and let's now train the network. Okay, so I also came up to the script here, and I decreased the learning rate because the self-attention can't tolerate very, very high learning rates. And then I also increased the number of iterations because the learning rate is lower. And then I trained.
Okay. I think the hard version of a softmax, argmax? Huh, I've heard that as well. Oh, okay, sure. Autocorrect. Just returns the biggest dimension. I'm gonna be quiet for a minute because of outside noise.
Trained it, and previously we were only able to get to up to 2.5, and now we are down to 2.4. So we definitely see a little bit of an improvement from 2.5 to 2.4 roughly, but the text is still not amazing. So clearly the self-attention head is doing some useful communication, but we still have a long way to go. Okay, so now we've implemented the scale.product attention. Now next up in the attention is all you need paper. There's something called multi-head attention. And what is multi-head attention? It's just applying multiple attentions in parallel and concatenating the results. So they have a little bit of diagram here. I don't know if this is super clear. It's really just multiple attentions in parallel. So let's implement that. Fairly straightforward. If we want a multi-head attention, then we want multiple heads of self-attention running in parallel. So in PyTorch, we can do this by simply creating multiple heads. So however many heads you want, and then what is the head size of each. And then we run all of them in parallel, into a list and simply concatenate all of the outputs. And we're concatenating over the channel dimension. So the way this looks now is we don't have just a single attention that has a hit size of 32, because remember, an embed is 32. Instead of having one communication channel, we now have 4 communication channels in parallel. And each one of these communication channels typically will be smaller correspondingly. So because we have 4 communication channels, we want 8-dimensional self-attention. And so from each communication channel, we're going to gather 8-dimensional vectors, and then we have 4 of them, and that concatenates to give us 32, which is the original n-embed. And so this is kind of similar to, if you're familiar with convolutions, this is kind of like a group convolution, because basically, instead of having one large convolution, we do convolution in groups, and that's multi-headed self-attention. And so then here we just use SA heads, self-attention heads instead. Now I actually ran it, and scrolling down, I ran the same thing, and then we now get this down to 2.28 roughly. And the output is still...
I think there's still some outside stuff. You can't hear it, but it requires me to be quiet. Yep, that might happen for another 5 minutes, so I'm sorry about that. Okay. I'll remain quiet and chat in the chat.
The generation is still not amazing, but clearly the validation loss is improving because we were at 2.4 just now. And so it helps to have multiple communication channels because obviously these tokens have a lot to talk about. They want to find the consonants, the vowels, they want to find the vowels just from certain positions, they want to find any kinds of different things. And so it helps to create multiple independent channels of communication, gather lots of different types of data, and then decode the output. Now going back to the paper for a second, of course I didn't explain this figure in full detail, but we are starting to see some components of what we've already implemented. We have the positional encodings, the token encodings that add, we have the masked multi-headed attention implemented. Now here's another multi-headed attention, which is a cross attention to an encoder, which we're not going to implement in this case. I'm going to come back to that later. But I want you to notice that there's a feed-forward part here, and then this is grouped into a block that gets repeated again and again. Now the feed-forward part here is just a simple...
Each time I'm pausing it, I'm like, are they still outside? I think not. I'll wait a couple more minutes, but I really am not... I think they're gone. I'm not saying that so that chat isn't chatting. I love the fact that chat is chatting. And I also had a joke to make
simple multi-layer perceptron. So the multi-headed, so here position-wise feed-forward networks is just a simple little NLP. So I want to start basically in a similar fashion, also adding computation into the network. And this computation is on a per node level. So I've already implemented it, and you can see the diff highlighted on the left here when I've added or changed things. Now before we had the multi-headed self-attention that did the communication, but we went way too fast to calculate the logits. So the tokens looked at each other but didn't really have a lot of time to think on what they found from the other tokens. And so what I've implemented here is a little feed-forward single layer. And this little layer is just a linear followed by a ReLU nonlinearity, and that's it. So it's just a little layer. And then I call it feed-forward, an embed. And then this feed-forward is just called sequentially right after the self-attention. So we self-attend, then we feed-forward. And you'll notice that the feed-forward here, when it's applying linear, this is on a per token level. All the tokens do this independently. So the self-attention is the communication, and then once they've gathered all the data, now they need to think on that data individually. And so that's what feed-forward is doing, and that's why I've added it here. Now, when I train this, the validation loss actually continues to go down, now to 2.24, which is down from 2.28. The outputs still look kind of terrible, but at least we've improved the situation. And so as a preview, we're going to now start to intersperse the communication with the computation. And that's also what the transformer does when it has blocks that communicate and then compute, and it groups them and replicates them. Okay, so let me show you what we like to do. We'd like to do something like this. We have a block, and this block is basically this part here, except for the cross attention. Now the block basically intersperses communication and then computation. The communication is done using multi-headed self-attention, and then the computation is done using a feed-forward network on all the tokens independently. Now, what I've added here also is, you'll notice, this takes the number of embeddings in the embedding dimension and the number of heads that we would like, which is kind of like group size in group convolution. And I'm saying that the number of heads we'd like is 4. And so because this is 32, we calculate that because this is 32, the number of heads should be 4. The head size should be 8, so that everything sort of works out channel-wise. So this is how the transformer structures sort of the sizes, typically. So the head size will become 8, and then this is how we want to intersperse them. And then here, I'm trying to create blocks, which is just a sequential application of block, 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 so that we're interspersing communication and feed-forward many, many times, and then finally we decode. Now, I actually tried to run this, and the problem is this doesn't actually give a very good answer.
There's some real cool conversation happening in the chat, and I can't participate because, according to my understanding, yeah, I will probably need to be quiet in a minute again. We'll see. We'll see how long this will last. Because I personally might, I don't know. I'll try to finish this, actually. Maybe 20 more minutes. Yeah. Yeah. So we are running around in a pitch dark. Okay, I'll be quiet now. This is fun.
Answer. And a very good result. And the reason for that is we're starting to actually get like a pretty deep neural net. And deep neural nets suffer from optimization issues. And I think that's what we're kind of like slightly starting to run into. So we need one more idea that we can borrow from the transformer paper to resolve those difficulties. Now, there are 2 optimizations that dramatically help with the depth of these networks and make sure that the networks remain optimizable. Let's talk about the first one. The first one in this diagram is, you see this arrow here, and then this arrow and this arrow. Those are skip connections, or sometimes called residual connections. They come from this paper, the Procedural Learning for Image Recognition, from about 2015, that introduced the concept. Now, these are basically, what it means is you transform the data, but then you have a skip connection with addition from the previous features. Now, the way I like to visualize it, that I prefer, is the following. Here the computation happens from the top to bottom, and basically you have this residual pathway, and you are free to fork off from the residual pathway, perform some computation, and then project back to the residual pathway via addition. And so you go from the inputs to the targets only via plus and plus and plus. And the reason this is useful is because during backpropagation, remember from our micrograd video earlier,
I have a feeling that Graham, our professor, talked about this. Dr. Graham, I guess.
addition distributes gradients equally to both of its branches that fed as the input. And so the supervision, or the gradients from the loss, basically hop through every addition node all the way to the input, and then also fork off into the residual blocks. But basically you have this gradient superhighway that goes directly from the supervision all the way to the input, unimpeded. And then these residual blocks are usually initialized in the beginning, so they contribute very, very little, if anything, to the residual pathway. They are initialized that way. So in the beginning, they are sort of almost kind of like not there. But then during the optimization, they come online over time.
I like the 3D visualizations of the models, like gradient descent. But I don't know if this follows the same structure. Run in the dark and seem to get somewhere that often seems pretty good. very high dimension space that have many data points. That's true. Sorted path, true, yep. It's intractable? What does that mean? So, that way. Does this have anything to do with tractors? Unmanageable, hard to control or deal with. Ah, cool.
And they start to contribute, but at least at the initialization, you can go from directly supervision to the input. Gradient is unimpeded and just flows, and then the blocks over time kick in. And so that dramatically helps with the optimization. So let's implement this. So coming back to our block here, basically what we want to do is we want to do x equals x plus self-attention and x equals x plus self.feedforward. So this is x, and then we fork off and do.
In the block, we have a forward, we have a self-attention and a feed forward. I'm trying to think how I can use that for the assignment. How I can cheat off of this from the assignment.
Do some communication and come back. And we fork off and we do some computation and come back. So those are residual connections. And then swinging back.
I'm really sure there's a different way to say we will have a different fork. Yeah, okay. In smaller samples. Ah, so we can visualize smaller versions maybe? That would be cool.
Up here, we also have to introduce this projection. So nn.linear. And this is going to be from, after we concatenate this is the size n embed. So this is the output of the self-attention itself. But then we actually want the...
Why is it n embed and n embed twice? Is it just...
to apply the projection, and that's the result. So the projection
We initialized it here?
is just a linear transformation of the outcome of this layer. So that's the...
I got lost right around here.
projection back into the residual pathway. And then here in the feed forward, it's going to be the same thing. I could have a self.projection here as well, but let me just simplify it and let me couple it inside the same sequential container.
Linear,
And so
ReLU,
this is the
linear.
projection layer going back into the residual pathway. And so that's, well, that's it. So now we can train this. So I implemented one more small change. When you look into the paper again, you see that the dimensionality of input and output is 512 for them. And they're saying that the inner layer here in the feed forward has dimensionality of 2048. So there's a multiplier of 4. And so the inner layer of the feed forward network should be multiplied by 4 in terms of channel sizes. So I came here and I multiplied 4 times embed here for the feed forward, and then from 4 times n embed coming back down to n embed when we go back to the projection. So adding a bit of computation here and growing that layer that is in the residual block on the side of the residual pathway. And then I trained this, and we actually get down all the way to 2.08 validation loss. And we also see that the network is starting to get big enough that our train loss is getting ahead of validation loss. So we start to see like a little bit of overfitting. And our generations here are still not amazing, but at least you see that we can see like is here, this now, grieve sync. Like this starts to almost look like English. So
also the structure of the output, it looks amazing. Like speaker speaking and punctuation.
Yeah, we're starting to really get there. Okay, and the second innovation that is very helpful.
I think we're out of the quiet tunnel. I think I can talk now.
For optimizing very deep neural networks is right here. So we have this addition now, that's the residual part. But this norm is referring to something called layer norm. So layer norm is implemented in PyTorch. It's a paper that came out a while back here. And layer norm is very, very similar to bash norm. So remember back to our Make More series part 3. We implemented bash normalization. And bash normalization basically just made sure that across the bash dimension, any individual neuron had unit Gaussian distribution. So it was 0 mean and unit standard deviation, 1 standard deviation output. So what I did here is I'm copy pasting the batch norm 1D that we developed in our Make More series. And see here, we can initialize, for example, this module, and we can have a batch of 32 100-dimensional vectors feeding through the batch norm layer. So what this does is it guarantees that when we look at just the 0th column, it's a 0 mean, 1 standard deviation. So it's normalizing every single column of this input. Now the rows are not going to be normalized by default because we're just normalizing columns. So let's now implement layer norm. It's very complicated. Look,
Having him say it's very complicated is really reassuring. No, you're not being obnoxious. No. You are being helpful. I mean that. It's like I'm reading it and sometimes I don't understand, but it is coming from the place of being helpful. So thank you.
Here, we change this from 0 to 1. So we don't normalize the columns, we normalize the rows.
Oh.
And now we've implemented layer norm. So now the columns are not going to be normalized, but the rows are going to be normalized. For every individual example, its 100-dimensional vector is normalized in this way. And because our computation now does not span across examples, we can delete.
Yeah, I don't feel familiar enough with some of the things, but there's a train of thought that one could follow.
All of this buffers stuff, because we can always apply this operation and don't need to maintain any running buffers. So we don't need the buffers. There's no distinction between training and test time. And we don't need these running buffers.
So this is from their Make More series. And since I haven't seen them, yeah.
First, we do keep gamma and beta. We don't need the momentum. We don't care if it's training or not. And
yeah, different models, not transformers, right?
This is now a layer norm, and it normalizes the rows instead of the columns. And this here is identical to basically this
seed that we gave it there. Yep.
So let's now implement layer norm in our transformer. Before I incorporate the layer norm, I just wanted to note that, as I said, very few details about the transformer have changed in the last 5 years, but this is actually something that slightly departs from the original paper.
Okay. Before I let him talk. We just implemented this with the self-attention plus making it multi-head. I don't think we made it cross-head attention. And now we're doing this normalization. We have feed forward, but I don't know if that, because all of this, too much. Yes. Okay.
Paper. You see that the add and norm is applied after the transformation. But
I don't know why there are so many people on Twitch. Why? Also, hi. I'm just a bit surprised. I didn't expect so many people to be on Twitch.
Now it is a bit more basically common to apply the layer norm before the transformation. So there's a reshuffling of the layer norms. So this is called the pre-norm formulation, and that's the one that we're going to implement as well. So slight deviation from the original paper. Basically, we need two layer norms.
Yeah.
Layer norm 1 is nn dot layer norm, and we tell it how many, what is the embedding dimension. And we need the second layer norm. And then here, the layer norms are...
Why aren't we putting this the same way that the structure of transformers is supposed to be? How do we put it together? That's weird and fun.
Applied immediately on X.
YouTube is less stress. Twitch is more fun. YouTube is more like, I'm a more YouTube user, but Twitch is more fun in a culture. Like it's culture.
So self.layer norm 1 applied on X, and self.layer norm 2 applied on X before it goes into self-attention and feed forward.
Aha. Okay, now that matches the structure. Maybe?
And the size of the layer norm here is an
Might have to wait today if the viewer count stays high. Oh, that would be cool. That would be cool.
embed, so 32. So when the layer norm is normalizing our features, it is the normalization here happens, the mean and the variance are taken over 32 numbers. So the batch and the time act as batch dimensions, both of them. So this is kind of like a per token transformation that just normalizes the features and makes them unit mean, unit Gaussian at initialization. But of course, because these layer norms inside it have these gamma and beta trainable parameters, the layer norm will eventually create outputs that might not be unit Gaussian, but the optimization will determine that. So for now, this is incorporating the layer norms, and let's train the model. Okay, so I let it run, and we see that we get down to 2.06, which is better than the previous 2.08. So a slight improvement by adding the layer norms. And I'd expect that they help even more if we had a bigger and deeper network. One more thing I forgot to add is that there should be a layer norm here also, typically, as at the end of the transformer and right before the final linear layer that decodes into vocabulary. So I added that as well.
Based on the structure.
So at this stage, we actually have a pretty complete transformer according to...
Yeah, 3 layer norms. Did we have an encoder or decoder? Do we have both, everything? Do we have all of them?
The original paper, and it's a decoder only transformer.
Yeah, that was what I was about to ask. It is decoder only, so we're only doing this side. We're not doing this side.
I'll talk about that in a second.
Because it's ChatGPT, duh. Okay.
But at this stage, the major pieces are in place, so we can try to scale this up and see how well we can push this number. Now, in order to scale up the model, I had to perform some cosmetic changes here to make it nicer. So I introduced this variable called nLayer, which just specifies how many layers of the blocks we're going to have. I create a bunch of blocks, and we have a new variable number of heads as well. I pulled out the layer norm here, and so this is identical. Now, one thing that I did briefly change is I added dropout. So dropout is something that you can add right before the residual connection back, or right before the connection back into the residual pathway. So we can drop out that as the last layer here. We can drop out...
No cross-section heads, of course. The heads that join the encoder to the... I see. Okay.
Here at the end of the multi-headed extension as well. And we can also drop out here when we calculate the basically affinities, and after the softmax, we can drop out some of those. So we can randomly prevent some of the nodes from communicating.
That's what dropout does? Cool.
And so dropout comes from this paper from 2014 or so. And basically it takes your neural net and it randomly, every forward-backward pass, shuts off some subset of neurons. So
now I'm questioning the randomness, but that would still be cool.
Randomly drops them to 0 and trains without them. And what this does effectively is, because the mask of what's being dropped out is changed every single forward-backward pass, it ends up kind of training an ensemble of subnetworks. And then at test time, everything is fully enabled, and kind of all of those subnetworks are merged into a single ensemble, if you want to think about it that way. So I would read the paper to get the full detail. For now, we're just going to stay...
Oh, whoa. Jeffrey Hinton is there. And Ayla. I know those 2 names. Should I know more? Toronto. Does Toronto have a PhD program that is distance learning? Please, anyone.
Stay on the level of this is a...
I'd like to see more from each company if they would teach it. Yeah, Anthropic. You're right. So this is ChatGPT. It would be cool to see other companies. I haven't tried to look for it. Maybe it could be out there. Probably they, because the Brooklyn Bridge paper is from Anthropic. Yeah.
Regularization technique, and I added it because I'm about to scale up the model quite a bit, and I was concerned about overfitting. So now when we scroll up to the top, we'll see that I changed a number of hyperparameters here about our neural net. So I made the batch size be much larger, now it's 64. I changed the block size to be 256. So previously it was just 8 characters of context. Now
there are now a few more players that are pretty loud, Anthropic being one of them, or maybe the only one. Yeah.
it is 256 characters of context to predict the 257th. I brought down the learning rate a little bit because the neural net is now much bigger, so I brought down the learning rate. The embedding dimension is now 384, and there are 6 heads. So 384 divided 6 means that every head is 64 dimensional as a standard. And then there are going to be 6 layers of that. And the dropout will be at 0.2. So every forward-backward pass, 20% of all of these intermediate calculations are disabled and dropped to 0. And then I already trained this and I ran it. So drum roll, how well does it perform? So let me just scroll up here.
Ooh.
We get a validation loss of 1.48,
Wow.
which is actually quite a bit of an improvement on what we had before, which I think was 2.07.
Is the difference only dropout? I mean, some hyperparameter changes, obviously that matters, but...
So we went from 2.07.
Yeah. Anthropic is big on understanding. It's there. I don't know how to read this, but okay. I'm a senior AI researcher. I got some interesting observations and claims, and one of it is that we do not need better algorithms for matrix computation. Human brains are much more inefficient for neural. We need good training data. That's true. We need good training data. Clean data, garbage in, garbage out, you know. You can never control what comes out, but you can control what goes in. Probably the fact that we can give it the whole internet and just not only not only intelligible things come out, that's pretty cool, but the cleaner data you have, probably the cleaner output there is. I think you're a first-time chatter, so hi. Frank L81. But I guess being open and for all humanity was open AI's thing, so maybe Anthropic is sticking to there is open AI started open and then became closed AI, so now Anthropic is like, I'll be the more open AI.
All the way down to 1.48 just by scaling up this neural net with the code that we have. And this, of course, ran for a lot longer. This maybe trained for, I want to say, about 15 minutes on my A100 GPU. So that's a pretty good GPU. And if you don't have a GPU, you're not going to be able to reproduce this. On a CPU, this would be, I would not run this on a CPU or a MacBook or something like that. You'll have to bring down the number of layers and the embedding dimension and so on. But in about 15 minutes, we can get this kind of a result. And I'm printing...
Wait, what were our hyperparameters? Same as the ones he's showing? No, different, smaller, way smaller. I should make them bigger and just run it for a longer time. Tech OpenAI co-founder announced new startup. Yes, we heard about it. The super safe, super Saiyan intelligence thing. Did you train on? Yeah, I did. I did the lazy version. I didn't do a not lazy. I can do a not lazy version on a GPU that I have some access to. I probably didn't even switch. I guess one model, I did it live. I don't know, but then the output was not there. I guess one model of automobile would be boring. So there are, oh yeah, there's that, but there, I mean, yeah, they are more about product with AI. mine is better and all that. Has me worried. This first company was open and went closed. Yeah. That's actually funny. This one is safe. Now what will happen? Oof. Yeah, is it 2026? Why? It should be a more cool number. Like, I feel like 2012 was a cool number for the world to end, but then it didn't happen. 2012 thing. There has to be a level of memeing happening. We've reached AGI. We will reach. Okay. I'll wait. I'll wait for that to happen.
Some of the Shakespeare here, but what I did also is I printed 10,000 characters, so a lot more, and I wrote them to a file. And so here we see some of the outputs. So it's a lot more recognizable as the input text file. So the input text file, just for reference.
Yeah. We'll wait for it to be proven. Have a low bar for AGI. I can say we got there in ChatGPT 2. With GPT 2, yeah. Why not? We passed the Turing test, so. No need to wait for it. It will not work with you. It will ignore you. That's fun. Okay. I don't need to be interesting. I'm fine. Oh yeah. Okay. Yeah. Dumb as a sack of hammers. I mean, sack of hammers still work though. Why should someone who is? Yeah. I mean, I understand the point of us being like ants to something that's more intelligent. Same day as landing on Mars and playing basketball. Are we landing on Mars in 2026? Because we already have some rovers there, and humans are not going there anytime soon.
Look like this. So there's always like someone speaking in this manner,
Cool.
and our predictions now take on that form.
Is that Hermione? When did Hermione become a Shakespeare person?
Except, of course, they're nonsensical when you actually read them. So it is every crimpty be a house. Oh, those preparation. We give heed.
Oh.
Oh,
servant. That's cool.
Oh ho, sent me you, mighty lord.
Wow.
Anyway, so you can read through this.
I'm sure you've had managers that were. I don't think I've had managers that were 10 times dumber, but I don't think I've had a dumb manager actually. I like all of my managers. The last age was about getting humans to be like machines now. It's about machines. True, that's pretty fun. Starship is still trying to leave Earth's atmosphere. Oh, Hermione's from the Winter Cell. Oops. I didn't know that. So J.K. Rowling stole it. Is Starship yeah, it's SpaceX. Okay. Cool. Good for them. I love the fact that we had the rockets returning to Earth. That is like an achievement that SpaceX did. So good for them.
It's nonsensical, of course, but this is just a transformer trained.
Only because you did follow. It says nothing about your intelligence following. Is Frank the assistant of the new AGI that is happening? Because like you're out there judging all of us. Like, okay, Coffee is a follower. Cool. Yeah.
On the character level for 1 million characters that come from Shakespeare. So it sort of like blabbers on in Shakespeare-like manner, but it doesn't, of course, make sense at this scale.
Cool.
But I think still a pretty good demonstration of what's possible.
Very much.
So now, I think
the way to make this better is more data and more training, right? That was not judging it. It was to claim. We followed the advice of them. I mean, we have to. Sometimes our livelihoods depend on them. Yeah. I thought you were the person that separates. But you know what? If AGI is there, they can do the classification themselves. Following CL is always clever. Wow, always be plugin, huh?
That kind of like concludes the
Does that make me the dumb manager?
programming section of this video. We basically kind of did a pretty good job of implementing this transformer, but the picture doesn't exactly match up to what we've done. So what's going on with all these digital parts here? Let me finish explaining this architecture and why it looks so funky.
It's cool.
Basically what's happening here is, what we implemented here is a decoder-only transformer. So there's no component here. This part is called the encoder, and there's no cross-attention block here.
This is really cute. The fact that it says decode on this side, encode on this side, that's actually really cute. I think it makes you super intelligent. Al Frank says... AI Frank, sorry. I read it as Al. AI Frank says, will doom us. I mean, we're already doomed. We've done the dooming a long time ago. We have doomed ourselves. Not by definition. Oh. I think it's a beaver, maybe? I'm not sure. Oh no. Such a super intelligent AI move.
Our block only has a self-attention and the feed forward. So it is missing this third in-between piece here. This piece does cross-attention. So we don't have it, and we don't have the encoder. We just have the
Coffee already told us we don't need the cross-attention.
Decoder. And the reason we have a decoder only is because we are just generating text, and it's unconditioned on anything. We're just blabbering on according to a given data set. What makes it...
This was for translation, right? The transformation requires both sides. By the way, what I'm using for the animated chat, Restream. Restream, I'm using it to character. Why did I see it as chat? Yes. I'm using a mobile app that's called ZEPETO, and it's basically like I'm sorry to say this. It's basically like Roblox, but your character is something like you can. It has a place where you create your character and then you can have it follow you as it's doing with me right now. Long-term attention is nice. And you can make it wear stuff. Have it be whatever face, whatever color, whatever, all of that. It's pretty cool. Yeah. Yeah, it's really cool. Like, I did not make any of this. It's all, and right now I have my phone in front of me and the camera is following what I'm doing. And I am feeding the mobile phone interface to my laptop and adding it to OBS. Yeah. Someday I will try to make oh, yeah. This is pretty 3D, but there's a version that's actually 3D. This is supposed to look like anime. So you can actually do it in this app if you want to. Are we talking about models or are we talking about long-term attention does not work already? So I get much variance. Sorry, I thought you were talking about characters. Okay. One with 3D? Three as in what 3 dimensions? So much variant. Oh, 3D characters. Sorry. Okay. I used the one that everybody else uses, but yeah. Yeah. I used the app that I forgot, the Japanese app, the thing that helps you model. I've done that before, but I find this one to be the easiest, and easy is fun. LDM from Intel. I don't know what that is. Right. Time is running out. Video has 10 minutes left, so I'll try to go through it a bit faster. Don't know what LDM is supposed to mean.
A decoder is that we are using the triangular mask in our transformer. So it has this autoregressive property.
The 3D model. Ah, cool. Sora. Where have I heard Sora? Mostly vision models capture pose. Ah. Yeah, traditional rendering techniques do the rendering of the... Yeah, there was an app that was discontinued. I keep waiting for... Oh, wow. Thank you.
Pusks just followed. CL welcomes you.
Thanks, Purple. Appreciate it. Thanks for the follow. We're now 111, which is funny. Latent diffusion model. Ah, no, it's not 110, it's 111. Cool. Not sure. Did not read much about it. Yeah, just using it. Yeah. There was one kaleidoscope that would actually track hands as well, but they stopped developing it. We reached the follower goal when Doohoo rated us last time. Yeah, I don't know if the congratulation things passed, like I didn't see it, but yeah. Yeah, this doesn't have tracking gestures, but it has built-in gestures. For example, I can do this. Oh, you can't see it because it's cropped off. Why is it cropped off? Oh, because anyway, you can't see it from here, but you can see it here because it's not cropped off here. Yes. Anywho, I need to go back there. And yes, but we passed that new follower goal. Now there's another follower goal. We will never be satisfied. MediaPipe has a hand tracking. I don't know. I can check that. So many people now get interested in math. Yeah, that's pretty fun. Have own a database system called Quaternion. It is the foundation of the first Omni models that can morph. Whoa, that's cool. Live. So they can hold many model representations. Well, data source. Most people do not know what I also did not know what that is. That's really cool. Ah, it's a thing. Ooh. Wow. Nope, don't know what that is, but that's pretty cool. Uh-oh. That scared me. Ah. Oof. 4D mathematical representation of rotation in 3D space-ish. Huh. Cool. Oh, I should remove the hand and go back to the other scene. There. Cool. I'll try to finish the video because I am 2 minutes overdue.
Where we can just go and sample from it. So the fact that it's using the triangular mask to mask out the attention makes it a decoder, and it can be used for language modeling. Now, the reason that the original paper had an encoder-decoder architecture is because it is a machine translation paper. So it is concerned with a different setting. In particular, it expects some tokens that encode, say, for example, French, and then it is expected to decode the translation in English. So you typically, these here are special tokens. So you are expected to read in this and condition on it. And then you start off the generation with a special token called start. So this is a special new token that you introduce and always place in the beginning. And then the network is expected to... Okay. So yeah, I've
seen Unity and the other thing that I don't even know how to read. Yeah, they use it to rotating. That's cool. Rotating floating point values. Wow. So I can use tokens. I need to revisit this whole lecture. Yeah, that's pretty cool, huh? The lecture. What I realize is that I need to go to the Make More series. But I don't know if I should. Anyway, yep. So many things to learn, so little time.
But neural networks are awesome, and then a special end token to finish the generation. So this part here will be decoded exactly as we've done it. Neural networks are awesome, will be identical to what we did. But unlike what we did, they want to condition the generation on some additional information. And in that case, this additional information is the French sentence that they should be translating. So what they do now is they bring the encoder. Now the encoder reads this part here. So we're only going to take the part of French, and we're going to create tokens from it exactly as we've seen in our video. And we're going to put a transformer on it. But there's going to be no triangular mask. And so all the tokens are allowed to talk to each other as much as they want. And they're just encoding whatever's the content of this French sentence. Once they've encoded it, they basically...
You should not learn it. What do you mean? I don't know what my conclusion was. Whoops, I'm lost. Let me just come to that. People have been using the... Ooh, I don't know what that is.
They come out in the top here. And then what happens here is in our decoder, which does the language modeling, there's an additional connection here to the outputs of the encoder. And that is brought in through cross-attention. So the queries are still generated from X, but now the keys and the values are coming from the side. The keys and the values are coming from the top, generated by the nodes that came outside of the encoder.
Yes. This part. Transformation instead of generation.
And those tops, the keys and the values there, the top of it, feed in on a side into every single block of the decoder. And so that's why there's an additional cross-attention. And really what it's doing is it's conditioning the decoding, not just on the past of this current decoding, but also on having seen the fully encoded French prompt, sort of. And so it's an encoder-decoder model, which...
The name is funny. Slurp. The spherical equivalent of linear interpolation.
Which is why we have those two transformers, an additional block, and so on. So we did not do this because we have nothing to encode. There's no conditioning. We just have a text file, and we just want to imitate it. And that's why we are using a decoder-only transformer, exactly as done in GPT. Okay, so now I wanted to do a very brief walkthrough of NanoGPT.
Oh, I created the first AI compiler stack 6 years ago. Huh. It was the first compiler that experimented with code refactoring. Whoa. Huh. Slurp and gulp. Works amazingly with via simplify error. Simple instructions. Wait. I think that joke, I didn't get that. I knew someone that swore they were getting amazing results, but it wasn't interesting. To me. No complex math. The complex part is the rule set. Ah. That's why you're saying good data gives good output. But I think people are like lazy now. They just want to give it everything and have good output. I think that Linux joke went over my head though. Is this gulp supposed to be something about the... I'm not sure.
Which you can find on my GitHub. And NanoGPT is basically two files of interest. There's train.py and model.py. Train.py is all the boilerplate code for training the network. It is basically all the stuff that we had here. It's the training loop. It's just that it's a lot more complicated because we're saving and loading checkpoints and pre-trained weights, and we are dictating the learning rate and compiling the model and using distributed training across multiple nodes or GPUs. So the training...
No current AI does come up with a correct rule set. My part is to design information so that you can train AI with to get the right result. So the key is the correct data set that teaches it to teach itself. Yeah, via self-experiment. I mean, if you try to equivalize it with humans, if you learn garbage, then why? Yeah. Okay, it's almost 2 a.m. Good night, JSS. We had fun. See you later, next time. Please, please, please go to sleep. 2 a.m. is too much. Also, you can go look at the moon before you go to sleep. Probably it's out. Maybe. There's a high likelihood that it's out.
.py gets a little bit more hairy, complicated. There's more options, etc. But the model.py should look very, very similar to what we've done here. In fact, the model is almost identical. So first, here we have the causal self-attention block.
I mean, time is relevant. Each of us are in different time zones, I'm sure. So yeah, for me, it's also morning, but yeah.
And all of this should look very, very recognizable to you. We're producing queries, keys, values. We're doing dot products. We're masking, applying softmax,
Nice.
optionally dropping out.
Nice.
And here we are pooling the values.
Nice.
What is different here is that in our code, I have separated out the multi-headed attention into just a single individual head. And then here I have multiple heads and I explicitly concatenate them. Whereas here, all of it is implemented in a batched manner inside a single causal self-attention. And so we don't just have a B and a T and a C dimension, we also end up with a fourth dimension, which is the heads. And so it just gets a lot more sort of hairy because we have four-dimensional array tensors now, but it is equivalent mathematically. So the exact same thing is happening as what we have. It's just it's a bit more efficient because all the heads are now treated as a batch dimension as well. Then we have the multilayer perceptron. It's using the GELU nonlinearity, which is defined here instead of ReLU. And this is done just because OpenAI used it, and I want to be able to load their checkpoints. The blocks of the transformer are identical, the communicate and the compute phase, as we saw. And then the GPT will be identical. We have the position encodings, token encodings, the blocks, the layer norm at the end, the final linear layer. And this should look all very recognizable. And there's a bit more here because I'm loading checkpoints and stuff like that. I'm separating out the parameters into those that should be weight decayed and those that shouldn't. But the generate function should also be very, very similar. So a few details are different, but you should definitely be able to look at this file and be able to understand a lot of the pieces now. So let's now bring things back to ChatGPT. What would it look like if we wanted to train ChatGPT ourselves, and how does it relate to what we learned today? Well, to train in ChatGPT, there are roughly two stages. First is the pre-training stage, and then the fine-tuning stage. In the pre-training stage, we are training on a large chunk of internet and just trying to get a first decoder-only transformer to babble text. So it's very, very similar to what we've done ourselves, except we've done like a tiny little baby pre-training step. And so
Tiny Shakespeare is pre-trained on Tiny Shakespeare, and you could fine-tune it on Tiny Sherlock.
In our case, this is how you print a number of parameters. I printed it, and it's about 10 million. So this transformer that I created here to create a little Shakespeare transformer.
Ooh, Tiny Shakespeare grew to be Little Shakespeare.
Was about 10 million parameters. Our data set is roughly 1 million characters, so roughly 1 million tokens. But you have to remember that OpenAI uses different vocabulary. They're not on the character level. They use these subwords chunks of words. And so they have a vocabulary of 50,000, roughly, elements. And so their sequences are a bit more condensed. So our data set, the Shakespeare data set, would be probably around 300,000 tokens in the OpenAI vocabulary, roughly. So we trained about 10 million parameter model on roughly 300,000 tokens. Now, when you go to the GPT-3 paper and you look at the transformers that they trained a number of transformers of different sizes, But the biggest transformer here has 175 billion parameters.
Oof.
So ours is, again, 10 million. They used this number of layers in the transformer.
Okay, but don't be late when you grab your 100K GPUs. Maybe grab 2 of them. 2, what are they called? The things where they're like rows and rows of GPUs? Data centers? I don't know.
This is the N embed. This is the number of heads, and this is the head size. And then this is the batch size. So ours was 65. And the learning rate is similar. Now, when they trained this transformer, they trained on 300 billion.
They can adjust the parameters unlimited. Will never give the right result. I mean, it's getting there. I don't think it. I don't know. No quantities, all clusters. Okay. Yeah, I guess it's. I don't know if it's about right questions and right answers, but it's doing a pretty good job, even if it. Yeah, even like with what it has right now. It only finds clusters of text in its dataset. That's not the right question. I see. I really understand your point, but I think what companies are doing are trying to not clean data, which probably is wrong. Oh, H100s. Oh, I see. 10,000. Needs logical thinking to get AGI. Yeah. Maybe we can train model to make clean data. How about that?
In tokens. So again, remember, ours is about 300,000. So this is about a million-fold increase. And this number would not be even that large by today's standards. You'd be going up 1 trillion and above. So they are training a significantly larger model
on more data.
A good chunk of the internet. And that is the pre-training stage. But otherwise, these hyperparameters should be fairly recognizable to you. And the architecture is actually like nearly identical to what we implemented ourselves. But of course, it's a massive infrastructure challenge to train this. You're talking about typically thousands of GPUs having to, talk to each other to train models of this size. So that's just the pre-training stage. Now, after you complete the pre-training stage, you don't get something that responds to your questions with answers and is not helpful and etc. You get a document completer. Right? So
document
it babbles,
completer.
but it doesn't.
That's not possible and not needed. We need to train it only the algo. Yeah. I think the effort to clean data doesn't get talked. Oh, I agree with you. You are. Yeah, no. But it is likely some secret source behind the models. He's not model is clever, ability to talk and make sense. Yeah, the sense, talk and make sense and understand part. Yeah. I might not be updated with the current research, but the fact that having clean data is ignored could be a possibility. Like we know the tokenization came from data cleanup gone wrong. Solid gold. Yeah, that thing. They actually have humans in poor countries. Yeah, annotating and cleaning data for cheap labor. That is true. That is very true. Like with the Amazon Mechanical Turk and all of that. Yeah. The thing about human data is that it's really messy. You can't turn it into like, I don't know, like even computer languages are more structured. Human language is very, very messy. with its audios and pictures and text and everything.
Babble Shakespeare, it babbles internet. It will create arbitrary news articles and documents, and it will try to...
Yeah. Try to post canting. Oh! Huh? Why do I know about it? Maggie Carp. I guess it's the most successful thing to play with at present are the multimodal. Where they interact with each other? Huh. Data was in the tokenization dataset, but was stripped out of training data. Just run spell check and grammar check and call it a day. Yeah. Why not?
Complete documents, because that's what it's trained for. It's trying to complete the sequence. So when you give it a question, it would just potentially just give you more questions. It would follow with more questions. It will do whatever it looks like some closed document would do in the training data on the internet. And so who knows, you're getting kind of like undefined behavior. It might basically answer to questions with other questions. It might ignore your question. It might just try to complete some news article. It's totally unaligned, as we say. So the second fine-tuning stage is to actually align it to be an assistant.
When you can simulate a complete growing society. Ooh. Can we do that? I don't know why Twitch chat is not coming into the here. 2 of the Twitch chats I could not see. YouTube chat is doing okay. Well, yep. YouTube chat is doing okay. You think you want to train models with spelling and grammar errors? Is that good data to keep? Even like, I don't have time to talk a lot, but like sometimes spelling and grammar corrections are even not to the level of, okay, you think this is an error, but it's really not, sort of situation. Language is messy. Model fine-tuning is not the solution, but that's what everyone is doing. Even for models, embedding perform not well when you use on-demand resource. You often go better with simple integrate data into the prompt. You don't want a model to be out of distribution when the user makes a typo. Okay, yeah, you're right. Fair.
This is the second stage. And so this ChatGPT blog post from OpenAI talks a little bit about how this stage is achieved. We basically, there's roughly 3 steps to this stage. So what they do here is they start to collect training data that looks specifically like what an assistant would do. So they are documents that have the format where the question is on top and then an answer is below. And they have a large number of these, but probably not on the order of the internet. This is probably on the order of maybe thousands of examples. And so they then find...
In a way, this is the good data, right? Like they have the trash data and then they make it fine-tuned on the good data.
Fine-tune the model to basically only focus on documents that look like that. And so you're starting to slowly align it. So it's going to expect a question at the top and it's going to expect to complete the answer. And these very, very large models are very sample efficient.
Yeah. Okay. Only correct format.
During their fine-tuning. So this actually somewhat works. But that's just step 1. That's just fine-tuning. So then they actually have more steps where, okay, the second step is you let the model respond, and then different raters look at the different responses and rank them for their preference as to which one is better than the other. They use that to train a reward model. So they can predict, basically using a different network, how much of any candidate response would be desirable. And then once they have a reward model, they run PPO, which is a form of policy gradient reinforcement learning optimizer, to fine-tune this sampling policy so that the answers that the GPT...
Yeah, they do have a reward.
ChatGPT now generates are expected to score a high reward according to the reward model. And so basically there's a whole aligning.
Yeah. It's like they tell it to be nice when they go and yeah, go into the real world. And do I skip that as my goal is to have the correct data on start? The thing about correct data is because you are talking about AGI, how can you find everything correct, you know? That would be really hard. Like you can have it be specific and like do one thing, one task, but for everything that would be hard.
Stage here, or fine-tuning stage. It's got multiple steps in between there as well. And it takes the model from being a document completer to a question answerer. And that's like a whole separate stage. A lot of this data is not available publicly. It is internal to OpenAI, and it's much harder to replicate this stage. And so that's rough.
Like having a real world model style. Abstract, obvious, and keep meaning. That would be cool. Probably there's research on that. I feel like they made the right choice for GPT-2 and 3, but now we have language models that do things like textbooks are all you need. Our language model refines the data. The language model itself refines the data.
Roughly what would give you a ChatGPT. And NanoGPT focuses on the pre-training stage. Okay, and that's everything that I wanted to cover today.
Ooh.
So we trained, to summarize, a decoder-only transformer following this famous paper, Attention is All You Need, from 2017. And so that's basically a GPT. We trained it on a tiny Shakespeare and got sensible results. All of the training code is roughly 200 lines of code. I will be releasing this code base.
Language model.
So also it comes with all the git log commits along the way as we built it up. In addition to this code, I'm going to release the notebook, of course, the Google Colab.
I don't know what alpha star is, but okay. Language model bootstrapping language model. First we train it on game data from tournaments, then we let it play against each other. Like AlphaGo. Oh, those alpha, the deep mind stuff. Got it. Real set that outperform humans.
And I hope that gave you a sense for how you can train.
It's probably one of the deep mind models.
These models, like say GPT-3, that will be architecturally basically identical to what we have, but they are somewhere between 10,000 and 1 million times bigger, depending on how you count. And so that's all I have for now.
Cool.
We did not talk about any of the fine-tuning stages that would typically go on top of
this person's last name is Chess. That's pretty cool, huh?
So if you're interested in something that's not just language modeling, but you actually want to, say perform tasks, or you want them to be aligned in a specific way, or you want to detect sentiment or anything like that. Basically, anytime you don't want something that's just a document completer, you have to complete further stages of fine-tuning, which we did not cover. And that could be simple supervised fine-tuning, or it can be something more fancy like we see in ChatGPT, where we actually train a reward model and then do rounds of PPO to align it with respect to the reward model. So there's a lot more that can be done on top of it. I think for now we're starting to get to about 2 hours mark, so I'm going to kind of finish here. I hope you enjoyed the lecture.
Thank you.
And go forth and transform.
Oh, that's so cute. He said go forth and transform. That's so cute. Your favorite game is StarCraft. I'm an old lady. I don't even know what StarCraft is. I'm sorry. And I hope you have fun with Stormgate, which is probably another game that comes out in 2 days, maybe. Or I don't know. The last game I've played, I don't know what. As it trains your, Google get free time to play StarCraft. No way. I mean, any game should. I don't want to make anyone mad, but isn't this like LOL? Like maybe this is older, but it looks similar. I think okay, yeah, probably these are like older ones and more. StarCraft is big in Korea. I know these games are big in Korea. That's why I was thinking about LOL because that's everywhere. Nope, it's RTS. First game came out 98. Highly competitive. Yes. I know World of Warcraft is also very competitive and is being played at a, like, yeah. I should shut up, but one of the idols that I liked interviewed someone that plays LOL. Why do I forget what it stands for? Help me. Because they just say Roru, and that's it. League of Legends, there we go. Anyway, that's why I know some about it. Like Warcraft 3. I know none of these games. Whoa. If that's slow. Wow. I have not played these games, and I probably shouldn't, because if I start, then I will never live my life. I tip my head to the people that can play games and live a normal life. Tip my hat, not my head. Why do I? Well, I tip my hijab, whatever. Okay, I have to run. Like, I am half an hour late to my next appointment. I'm kidding, but I'm late. I'm really late. I shouldn't have streamed for 2 hours, but I did because I wanted to finish the video. Thank you so much for Frank for being. Running is great. Running is good for the health. Aw. Oh, Hichu praise lol. I love Hichu. Ed, you've been here the whole time. You were a bit quiet, but that's cool. Thanks. Raid and run. Who should we raid? Anyone have any idea about who we should raid? Because I gotta run. Do we have anyone? Should I go to Twitch and see if the people I'm following are online? Flash mob, yeah, huh? Order 1,000. Why not? Cheeseburgers. Is anyone cool? There is one person that I follow that is online. Should we rate that person? I think they. I think did I? I don't. Did I rate their channel before? Because I don't want to be. I like them. I mean, I follow them. Ooh, that person? I don't know who that person is. Should I search? I am late. I'm late. I am really late. Help. Oh, God. Help. No, my second screen just went off. It's off right now. I can't see anything. Now I can see some things. Fallout. Huh? I don't know that person. Should we? Is it okay if we rate them? Oh, they're doing something with C. ++. Why not? What'd I do? Nothing. Okay. Help. Maybe just time enjoyed just looking at software and game dev sections. Huh? He does a game mod. I don't know. Help. Ooh, they have a lot of views. I'm afraid to go there. But they seem. I'm scared. No, that one is scaring me. Sorry. Too many people. I'm a baby. Good talker. Nope, definitely not going to someone with 100 views. That I thought that one is a big channel, but now I'm like, no, this is cool. So I'm gonna try that quantum one, and I gotta just run. So let's try raid. Did I forget how to raid? Raid channel. And thank you for being here. Really appreciate all the chat. Goodbye. Thank you. Thank you. And we go. Maybe in 5, 4, 3, 2, 1. I don't know. How much do we have? Yeah, thank you. Thank you for stopping by. CL raid is on the way. Did we go? Oh, I should press raid now. Okay. Bye.